Hello everyone. So today we are going to discuss about how caches work and different schemes uh, to access the data in caches. So usually we will discuss of the simple cache design. So caches are divided into blocks and which may be of various sizes. So the number of blocks a cache is usually a power of 2. So for now we will say that each block contains 1 byte. Um, so here is a cache. So with the 8-bit data. So each block size is 8-bit data. So usually we have 4 important questions. So whenever we copy a block of data from main memory to the cache, so where we have to put that data. So that is the question number 1. And question number 2, how can we tell if a word is already in the cache or if it has to be fetched from the main memory first. So eventually the small cache memory might fill up. To load a new block from main RAM, we have to replace one of the existing blocks in the cache, and which one we have to replace, again that is also one more question. Fourth is, how can write operations be handled by memory systems? So we will answer all these questions one by one. So one of the simplest approach is direct map to cache. So in each memory address maps to the exactly one cache block. So here is a memory address. So it's a 16 byte main memory and a 4 byte cache for 1 byte block. So this is your cache and this is your memory. So 16 bytes. So each block is of 1 byte. So memory locations 0. If you observe here, memory locations 0, 4, 8, 12. So it is marked with color red. All map to cache block 0. Okay, same color. Similarly, addresses 1, 5, 9, 13 map to cache block 1, that is in blue color. But how we have computed this one? So here it is. So one way to figure out is each cache block, a particular memory address should go to use the mod operator. So if the cache contains 2 raised to k blocks, so in this case we have 4 blocks. Okay, then the data at memory address I would be go to the cache block index. For example, I mod 2 raised to k. For example, if you take 14 and we have 4 blocks, so 14 mod 4 is 2, so it is mapped to cache block 2. And similarly we can represent memory address in the binary form. For example, 0 you can write in 000, and this is 1, this is 2, 3, 4. So like that we can write up to 0 to 15. This is 16 byte memory. Similarly we can do indexing for cache as 0001 in the binary format. So now the question is, how can we find the data in cache? The second question was how to determine whether or not the data we are interested is already stored in the cache. So if you want to read memory address I, we can use the mod trick to determine which cache block would contain I, but other addresses might also map to the same block. Okay, so for example 0 and 4 both can be mapping to the same address. So how to distinguish between them? So for instance, cache block 2 could contain data from addresses 2, 6, 10, 14. So all are mapping to cache 2, but it is very difficult to, if you look at the, suppose look at the data at index 2 in cache, so it is mapping to 2 as well as 6, it was 10 as well as 14. So we have to remove the confusion here. For that purpose we need to add tags to the cache. So this is a tag, so we are adding tag to the cache which supply the rest of the address bits to let us distinguish between different memory locations that map to the same cache block. For example, if you see here, we have a index of the cache, so the lower order bits of the memory like 00, 01, 10, 11. So this is an index, and this tag side, if you observe here, first block 00, so upper bits of the address, memory address are used as a tag here. So 00, so this belongs to first block here. Similarly, we have 10. If you observe here, 10 lower bits of memory address. Okay, so 10 is there, and tag, if you observe here, this is 01, so we are writing here 01. Similarly, for 11, we have 01 as the upper bits of memory address, so we can use it as a tag. So if you similarly observe for 01, what will be the tag? So if you go to 01, okay, so this is your 01. So tags, if you observe here, the 01, so tag will be 11. Okay, so this is how exactly it looks. So we have a cache with index and a tag and data. So if you add tag plus index, we will get the main memory address. For example, here 0000 we will get main memory, and similarly 1101 will get uh, uh, 1101. So we can add tag plus index, will get main memory address. So one more detail we have to add, whether the data stored in cache is valid or not. So that is done with help of valid bit. So whenever the cache is empty and does not contain valid data, so initially, so we should account for this by adding a valid bit for each cache block. So here we are adding one valid bit. So when the system is initialized, all the valid bits are set to 0, initially to all 0. When data is loaded in particular cache block, the corresponding valid bit is set to 1. So if data is loaded to a particular cache block, the corresponding valid bit is set to 1. For example, here this valid bit is 1. So main memory address in cache block, so this is 0. So it is a valid one, and if you observe here, valid bit, it is 0, so it is invalid. Similarly, this one 10 address, this is also invalid, and this one is valid. Okay, so only, so what happens whenever we get data in the cache, so this is called as a cache hit. So when the CPU tries to read from memory, and the address will be sent to the cache controllers, the lowest k bits of the address will index a block in the cache. For example, this is your address, 32-bit address, and by the CPU. So the upper 22 bits are memory address, and next 10 bits are used for yeah, cache, identify cache blocks. Okay, and lowest k bits of the address will index a block in a cache. So here lowest k bits, k is equal to 10 here, and if the block is valid and tag matches the upper m minus k bits of the bit address, then the data will be sent to the CPU. So if you see here, so address So this is called as a tag. Tag will come here, and this tag also matched. So the cache tag and address sent by the CPU both are matched. If it is matched and valid bit also it is checked, and this is given to the AND operation. So if it is 1, then it is a hit. Then the data is given back to the CPU. Okay. Similarly, we how to load the data or block it to the cache. So after the data is read from the main memory, putting a copy of that data into cache is straightforward. So the lowest k bits of address specify cache block. So this lowest k bits. So k is equal to 10 here now. The upper m minus k address bits are stored in the blocks tag field. So this is your 22 is stored in the tag field. So the data for main memory is stored into blocks data field. Okay. So if you see here, this tag address we will have to match. Okay, and we have to store the data. So this is a simple example of direct mapping example. So here the CPU will issue the memory address, so that a memory address is compared with the tag in the cache, and if both matches compare, if it is both are equal, then we will generate a hit in the cache. Okay, otherwise it is a miss in cache and block in frames, so it will be fetched from the main memory because data is not available here. So this is how direct mapping cache organization is there. So b0 for main memory is mapped to b0, and similarly b1 is mapped to b1. So block 0, block 4, block 8, block 10 are mapped to b0. Okay, similarly we can map b1 to b1 and b5 to b1. So this is how the organization is done in direct mapping. So one more type is there, a fully associative cache. A fully associative cache permits data to be stored in any cache block instead of forcing each memory address to a particular block. So when a data is fetched from memory, it can be placed in any unused block of the cache. Okay, so there will never a conflict between two or memory addresses which map to a single cache block. Okay, so one of the main problem is expensive to implement because there is no index field in the address anymore. The entire address must be used as a tag, increasing the total cache size. So if you see here, address 32 bits, whole 32 bits used as a tag, and cache tag 32 bit we have to. So earlier it was only k bits, only we are using the last 10 bits for mapping, but now we are using it for the next whole tags, so we need more comparators. So hardware level complexity is more compared to the direct associative mapping. If you see here, block 0 can be mapped to b0, can map to b1, it can map to b2, it can map to bf3. Similarly, b1 can be mapped to b0, b2. So like that we can write. So b15 as also can map to b0, b1, b2, b3. So there is no restriction that you have to place the cache in memory block in particular cache block. Okay. Similarly, we have a one more type of cache organization, that is set associative. So the cache is divided into the cache is divided into groups of blocks. called sets, and each memory address maps to exactly one set in cache, but data may be placed in any block within that set. So if each set has 2 raised to x blocks, the cache is an 2 raised to x way associative cache. So for example, here one wave associative 8 sets, one block each. So this is simple one way associativity. Okay, so we have one block in 8 sets, so each set contains only one block. That's why it is called as one way associative. So two way associative, 4 sets here have 2 blocks each. So here I have set 0, it has 2 blocks. Set 1 is also having 2 blocks. Set 2 and set 0 is also having the 2 blocks. That's why it is called as a two-way associativity. Similarly, we can have four-way associativity. That's 2 sets, 4 blocks each. Okay, so usually if you have a address bits, so so address is usually dot assume that it has m bits, and out of that m minus s minus n is used as a tag, remaining s is used as a index, and n is used as a block offset. And suppose if you want to get a block offset, then memory address mod 2 raised to n, and if you want to get the block address, memory address slash 2 raised to n, a set index, then block address mod 2 raised to, as these formulas can be used to access the data from cache. Thank you.